let's get a wall up here. So wall. This wall is different to the previous one because I now have an air gap here between two layers of brick. So the building material is the same as last time, but I have this air gap. So, how does this change the process of conduction? Well, whereas in the previous one, it just the molecules on the outside of the brick were caused to vibrate faster with larger amplitudes, and then those vibrations were passed on through the brick. Now we have this air gap. So for the vibrations to get from the outside of the wall to the inside, they're going to have to pass those vibrations, or that vibrational energy, through the air molecules. But that's difficult. Firstly, we can look at things from the thermal conductivity point of view. Air has a lower thermal conductivity value than brick. Thermal conductivity values tell you how good a material is at conducting. Let's get the thermal conductivity value for air, 0.023. Thought 0.0023 is too small. That's watts per meter per Kelvin. That's less than brick, which is 1.31 watts per meter per Kelvin. So that's the first thing we can say about it, that because air has a lower thermal conductivity, conduction is reduced from the brick to the air, through the air, and from the air to the brick. So, the next thing which is important to say as well is to refer to the molecular spacing. Now, air molecules are more spread out than the molecules in brick. So that means that it's harder to pass on that vibrational energy, or that when the air molecules collide, to pass on their kinetic energy. So that's what we need to say here. Because the air molecules are so far apart, they hardly collide with each other at all, whereas the brick molecules are closer together, so they can pass those vibrations on to neighbouring molecules more easily. That's actually why it has a lower thermal conductivity value than brick, the air. So we need both things in the answer there. Okay, next, now because we've introduced this air gap, there's the possibility of convection taking place in our wall, because air can convect. However, it's designed to reduce convection because it's so small. Because it's so small, the air is trapped. And what it does is that prevents convection currents being set up. So sure, you can have a big gap there, apart from that using up more space. That would also allow convection currents to be set up. So by keeping the gap small, we keep the convection to an absolute minimum, or completely eliminate it. So that's all we need to say there. That's how heat transfer is reduced by convection. I'll just write that down there. Okay, and then we have radiation. This is not to do with the cavity, but it's to do with the paint on the wall. So if we have our wall here, just looking at it as a whole, and there's paint on the outside here. Now, thermal radiation coming in, or the infrared radiation coming in here, can pass through ordinary paint. How much depends on the emissivity value. So what we talk about here is emissivity. And ordinary paint has a value of 0.92. The way to understand that number is if you multiply it by 100, it tells you what percentage of the incoming radiation is transmitted through the wall. So if we have 100% coming in, this tells me that 92% will go through. This is transmitted. Let's just write that there. 92% is transmitted through the wall. What happens to the remaining 8%? 100 minus 92 is 8. That's reflected. So a very small amount of the incoming infrared radiation is reflected, most of it goes through. So ordinary paint is not very good at preventing heat transfer by radiation. If you have low E paint though, so we've got another wall here, and this has low E paint here. Low E paint has an emissivity value of 0.58. So again, multiply it by 100 and that tells you how much percentage will be transmitted. So we have an incoming 100%, 100 times 0.58 gives me 58%. So that's a lot lower than the transmitted value for ordinary paint. And then the remainder is reflected. That's 42%. So you can see that the amount reflected by the low E paint is much larger than for the ordinary paint. So that will do as an explanation for how heat transfer by radiation is reduced. It's reduced because low E paint reflects more of the incoming radiation. So that'll do for P3 in 14.4. We've looked at 3 heat transfer processes through a wall and then inside a room. So we're explaining those processes, and then we've applied them to some situations where we're trying to reduce heat transfer by conduction and convection, and then by radiation as well.